So now we continue, and now we look on operator A as operator in L2 on the torus, and we can write this operator as a sum of two operators. Yeah, the first one is integral operator, and the second is operator on the multiplication of the function. So this A psi minus Q M Q kappa 1 Q dq minus, I write in this way, kappa 1 psi, and G is a function which is equal to integral in RD, yeah, A psi minus Q Q dq. And using that, the function mu is bounded by two from below and from above by a positive constant, and the integral of A is again constant. We can conclude that this function is also between two positive constants. Sorry. Okay. So we have for the operator A the following representation. A is a sum of integral operator K, let it be operator K Q1, K minus G Q1. So there is operator of multiplication on a good function, and here is integral operator. What we can say about this operator? This operator will be compact in L2 on the torus, and it is one of the main statements. Why it is compact? Let me explain. First of all, we can see that it is bounded operator. We use here only that function A is a function from L1, in fact. And we have the following estimate. Maybe I write here. So if I'd like to estimate this function, then it is some constant. For mu we have constant alpha 2. Then there is a norm of operator L in L1 and norm phi in L2 on the torus. As I understand, you know this estimate, and I don't need to prove it. Actually, it is very simple. It is like a good problem for students. It is important that here in the estimate, in the bound, we have a norm of the function A in L1. And after that, we can consider the truncation. Truncation for A. So if we consider the integral, so we can consider operator Kn, which is defined by the function an psi minus q. Mu is just, yeah, we can remove this function. Mu, it is not so important, but okay, yeah, it is better to keep it. Q dq in Rd. Then this operator is compact, yeah, because we consider truncations. An is a function A times to indicator of the function minus n d. And this operator compact. And if we consider now the norm of the difference k and kn, then using this estimate we have that it is less than some constant norm of the a minus an in L1. And of course, this tends to 0. So we have the result that operator K is a limit operator for the compact operator. So we have convergence in norm for these operators. And the limit, then the limit, of course, there is compact operator. it is very important statement for us. So one operator is operator of the multiplication on a good positive function, and another operator is compact operator. In fact, it is one of the main steps in our consideration that this operator compact, and then we can use again Fredholm theory, the Fredholm theory, because this operator is operator of the Fredholm time. We can consider this K. Yeah, let's consider this operator as the following operator, and it is, since it's bounded operator, of course there is again compact operator. And now we can reformulate our equation as a solvability condition. Yeah, we'd like to find. Yeah, first of all, we know that the operator A has one. Actually, this operator is a generator of Markov jump process. For this operator, we know that only one function belongs to the kernel of this operator. There is constant function. Then we have the same for the adjoint operator, and for adjoint operator, the kernel of the adjoint operator, it is just a function mu. It is easy to check. There is function mu, because yeah, you can see that if we put here mu, then there is symmetric kernel for this operator. And then the solvability condition for our equation. So we have equation.
One more.
Just if psi. Just a second. So we have the following equation, and we'd like to get an answer about existence of function psi. Yeah.
One more.
I see. I think maybe you have remark. Okay. And then to prove that there exists function kappa 1, we should check the solvability condition, and solvability condition is the following, that function phi should be orthogonal to the function mu from the kernel of the adjoint operator, right? So the solvability condition can be written in the following way. If psi mu psi d psi should be equal to 0.
Integral over the torus.
Yeah, because because we consider now a function in L2 on the torus.
Obvious that the kernel of the adjoint operator consists of.
Yeah, because we know for the direct operator, it is a generator of the Markov semigroup, and for direct operator, we know that this operator has only one function. Here, the uniqueness comes from the direct operator.
Why it's mu? Because if we multiply this equation by mu on psi, it's getting symmetric. And if it is symmetric, then the kernel of adjoint coincides with the kernel of this. But since you multiply by mu, mu kernel is not.
I'm sorry.
Now. So for the adjoint, it's also mu.
I'm sorry. So the question why it is mu? Okay, just a second. Then I rewrite. What is equation? What is a adjoint operator? Maybe I write, and then it will be clear. Operator A adjoint phi psi.
It's about lambda mu. They can have zeros. It's not important.
No, in this theory it's important that they are positive.
They are positive. Lambda mu.
Yes. Between two positive constants.
Q.
But then you can probably include them.
Q minus.
They depend on epsilon and you build.
I see.
Phi. What is the adjoint operator? So we change. A is symmetric function. Yeah, we assume that it is symmetric function. So the adjoint operator has the following form, and it is easy to see that only one function at least one function. When we take phi is equal to mu, then we have here 0. Yeah. Okay, and yeah, and another, then we use symmetricity, and we will see that the quadratic form of A kappa kappa will be symmetric with respect to the scalar product where mu is the weight. And it is unique due to uniqueness for the direct operator. Okay, and now look, if now we should check this condition, and what we have now, function f psi is the following function, and now we should integrate over Td with function mu psi, yeah, here, mu psi dq d psi.
What is c minus q? It is somebody's argument.
It is linear function.
It is here.
No, in fact, there is vector, yeah, because we are in RD, but yeah, it is linear function in each component.
Because C is replaced by.
In fact, I'm sorry. I should say that kappa 1, the first character, there is vector, yeah. It is not one function. There is element of L2 Td d. Because of C, we have here vector. Here is vector. Here is vector. Here is vector. But what is important that each component of this vector has the same structure. They are not coupled. So we can consider for each component of the character of this vector function the following equation. Of course, there should be j and should be j here and should be j here. Yeah, thank you very much, because I forget about this thing. By the way, this function, there is matrix function, so be careful. Okay, and yeah, and how we can see that it is 0? It is
nice exercise for you.
Yeah, it is good exercise that it is 0.
Symmetric, anti-symmetric.
But again, so this is sort of because mu is, but you already said, but I'm afraid I missed. So why there is no other elements of the kernel?
Because for direct operator, it is effect from, for example, probability theory.
Dimension.
No, there is only constant function which belong to the kernel of the direct operator.
Yes, this is what I'm saying. The dimensions should be 1.
Yeah. Why this kernel is one-dimensional? Yeah. Okay. Yeah. In fact, here we use very simple lemma, but very useful. That okay? Maybe I formulate it here because we need this lemma now. So if we have function which satisfy the following form, and lambda and mu periodic function, then integral of the double integral in RD and on the torus bx minus y lambda x mu y dx dy equal to minus bx minus y lambda y mu x dx dy. So that means that we can change variables in, actually you can consider any kernel, but yeah, for our kernels, that means that we can change variables x and y, and then the integral is equal to the integral with sign minus. And here we consider this periodic function in such a way that if we consider this function in RD, then of course we consider the periodic extension of this function. And due to this fact, we can change variables for this function, consider this function or on RD, either on the torus. There is some small trick, but yeah, here we, by the way, here we can use this lemma and we just have 0. Okay, so what we obtained? We obtained that in our situation, solvability condition holds, and that means that there exists function kappa 1. There is a function from L2 on the torus, and what we can conclude in this way, that this term disappears. Great. We don't have this singular term. But what we can say about the next term? Again, we have some equation now on the second character. And now we look what we can say about this one. And I'd like to stress that in this case, the second character is a matrix valued function. Yeah, because here we have matrix. We have matrix here. Everywhere we have matrix. So again, for each component of our matrix, kappa 2 psi. So there is function in L2 d square. So maybe I missed this index, so we should consider here ij. And we have again the equation with the same left-hand side, with the same operator, which is a sum of compact operator and operator of the multiplication on a good function. And in the right-hand side, we have the following expression.
So now it is kappa 2?
Yeah, now it is kappa 2. Yes, it is kappa 2. And
you don't want it to be 0 now, no? You don't want it to be
yes,
0.
it is not possible now to find, because now we have at least this function. I don't know why it is not. It is clear why it is clear that it is not possible that. But if it is 0, then it is not.
No, it's of course it is not 0.
It is not 0 by the following, because you see here is periodic function, and here is a growing function, so it cannot be compensate to each other.
No, but the point is that you want to have it. You want to have an approximation called form a solution, right?
Yeah.
Or the percent.
Just continue.
Yes, I'd like to obtain the limit differential operator. That's right.
Yeah, you want this term to...
Stop your mystification.
Okay, so what we have here? Have integral in RD. Just ask a question, yes. Xi minus Q minus, yeah, minus 1/2 Xi minus Q plus Xi minus Q kappa 1 Q, yeah, kappa 1 Q. Okay. Yeah, and now again let us write the solvability condition, and in this case solvability condition, so there is function, let it be g xi, and again the solvability condition reads in the following way. integral g psi mu psi. So we don't expect that it is 0. Yeah, this integral should be 0, but we'd like to obtain that it is d psi is equal to some, sorry, there is also lambda. There is lambda here, of course. But okay, without lambda, let us assume that it is just integral for function. Okay, there is some constant theta mu psi d psi.
That's the way to introduce the matrix Q, yeah?
Yeah. So what I'd like to say that if we consider the difference with some constant theta ij, yeah, for some ij, then in this case I can write the solvability condition in the following way. Then of course it can be this condition. Maybe I write it here. So now the next step is to define the family of this theta ij and prove that in fact this family defines the matrix which is positive definite. So that is the next step. Okay, so maybe just use again. Okay, so I use this expression Tij. So if you remember, I have this lambda before, and in fact, what I'd like that lambda on psi should be equal to mu, or to theta. So eventually my equation on the matrix theta has the following form: mu psi lambda psi d psi. Let it be theta tilde is equal to the integral over TDRD a psi minus q mu psi mu q 1/2 psi minus qi psi minus qj minus psi minus qi 1jq d psi dq. So there is some constant because so if I'd like to find to prove that matrix theta is positive definite, that it is the same as to prove that matrix theta delta tilde also positive definite. So I will consider only this matrix, and in fact it is enough to consider the symmetric part of this matrix only to prove that it is positive definite, and the symmetric part is equal to the following. So if I write the sum ij plus jy, then I don't have 1/2 here, but I have here minus psi minus qj kappa 1I q, and here is d psi dq. And again, the next problem is to prove that this family of constant, which is constant, yeah, there is constant, they define the positive definite matrix.
I'm a little bit lost. So that is defined by the intermediate equation.
Theta is defined from the solvability condition.
Yes, so
to find the second part, the second.
Yes, but then I kind of plus and minus, and I already find kappa 2, so that the whole this integral is this theta.
Yeah, we can find.
Yeah, this gives
sorry.
The existence of kappa 2. But in order to, at the end, we need positive definition of matrix.
But still.
It is, yeah.
It is this solvability, it is this kind of intermediate equation. So you have three equations on this. It is this. Oh, you erase exactly the one which I thought is the definition of that. No?
Okay. Yes, the definition of theta is the equation of the solvability. That the right hand side of this our equation on kappa second should be orthogonal to the kernel.
Yes.
Should be orthogonal function mu, and after this condition we obtain this expression for symmetric part of matrix theta up to the some constant. Yeah. So how to prove the positive definite? Now just I should explain the main idea. I try to explain the main idea. Okay, let me stop at any place when you understand that it is enough. So, in fact, what I'm going to do to prove that this expression is exactly the same as the following expression, which is for sure positive definite. What is this expression? We'll compare. I don't.
You can lift up
Okay, yes. Очень хороший, да. So. Component with index I, and there is the same component with index j. dq d psi. So for this matrix, of course, it is clear that this matrix is positive definite. And what we do, in fact, is again very technical things. We prove that the expression on the top is exactly the same as expression on the bottom. Not exactly on the bottom, but here. And how we prove it? I think that I just explained the main idea. So the first term, you see that the first term coincide, yeah? So we can consider this is this one. Okay, and it is the same as the first term in the expression on the top. And for other terms, we use our lemma. Yeah, we can use this lemma on the real top. And in fact, we use some modification like to this one. For example, I just explained on the example of one of the integrals. So let us, if we consider the integral of the following form, xi mu q, psi minus q, j kappa 1 I psi d psi dq, then it is the same as minus there is integral in torus and in RD. Then, using this lemma and using the fact that if we take B as this function, then we have a xi minus q. There is symmetric part, there is symmetric part, it is the same. Xi minus q. And here is kappa 1q d xi dq. And using this equality, we made modification inside of integral corresponding to E, and eventually obtain that this integral coincides with the integral on the top. Another very important also remark that we also use here the equation on the first correlation function. So we use this one, plus we use expression, this equation on the first correlation function. So that the integral of A mu kappa 1 q minus kappa 1 xi d xi is equal to A xi minus q mu d dq. But I'm sorry, it is two technical things that it is. I prepared for my lecture, but I think that it is better to miss. But if you have question, I explain all this.
Stupid question. So, but mu, are they positive mu?
Mu positive, sure.
Yeah,
Sure, positive, and it is even bounded by the positive constants.
Why is this I is positively definite?
Yeah, sure. So, after the calculations, we assume that we convinced, and so we proved that the corresponding matrix theta is positive definite. So that means that we can write our expression for L epsilon V epsilon in the following way. Yeah, so eventually we obtain this very important thing. And now the last step in our calculations. So we would like, but I think it is very typical. Yeah, the next is very common step. The last step, we consider two equations with the same function f. And first we assume that function f from the Schwarz space. Then we can use our lemma, and we can write that. Just a second. So first we can, from this equation, we can write that our function u0 is also from the Schwarz space. And using this function u0, we can construct the corresponding ansatz, which depends, okay, I write it like ansatz for the function u0. And so, in fact, I'd like to show that u0 and u epsilon are a function which are close to function v w epsilon. What I proved now, and after that we prove that both of these functions are also close. So for function u0, I can construct the corresponding ansatz, and by construction of my ansatz, sorry. Sorry, I should write it again. V epsilon is equal u epsilon plus epsilon kappa 1 x epsilon gradient u plus epsilon square. So you can see that this function, of course, close. Yeah, so it means that v epsilon tends to u0 when epsilon tends to 0 in norm of L2. maybe I write it here in this way. V epsilon minus O epsilon in L2 tends to 0.
U is U naught?
Yeah, U 0, yeah, U naught.
In this
It is
W epsilon, U is U naught?
Yeah, it is exactly
Yes,
U
yes,
это
yes.
U ноль.
U 0, да.
Everywhere, not only in the
I'm sorry. I start. Yeah, because this function has a finite norm in L2. And for the function W epsilon, we have L epsilon, V epsilon, by this lemma, yeah, we have that it is equal to theta U epsilon plus V epsilon. So, okay, there is L 0, U 0 plus V epsilon. Then we can conclude that L epsilon minus M W epsilon is equal to L0 minus M U 0, U dot, yeah? U dot правильно. Dot. Plus some other function, phi epsilon, but again with a small norm. So we have F here plus phi epsilon. And what is F? F is, sorry, just write here something. Yes, and F is exactly from the first equation. It is L epsilon minus M U epsilon plus C epsilon. So we have this equation, that this equality. And since operator L epsilon minus M for this operator, for the resultant of the operator L epsilon, the following estimate, it is bound, the following estimate which is uniform in epsilon is valid. There is some constant divided on M. There is positive operator, we know. Then we can conclude that V epsilon and U epsilon also close, in the sense that V W epsilon minus U epsilon also tends to 0 when epsilon tends to 0.
But again, I missed a little bit. Where this inequality is from? This one?
Yeah, because L epsilon, you see, L epsilon, yeah, it's operator. It is, if you consider the quadratic form, it is positive, yeah?
We can
so
symmetrize
it is, yeah, I explained that if you consider a special, you consider L2 with the weight which is equal to mu divided on lambda, then in L2 with this norm it is symmetrized. But this function is bounded by two constants. So the spectrum of both of these operators are similar.
Maybe you should also explain that for symmetric kernel it's equivalent to the quadratic form. Write down the quadratic form.
Yes, so for any M, we have resolved that. So if M is not 0, it is not
So if I consider LOO with respect to this weight, with respect to this measure, yeah, then I have A. Okay, I can write it just like okay, psi minus eta. Lambda will be disappeared, so it will be mu psi mu eta. And here is U, okay, y minus ux dy
square, yeah?
Maybe I write
No,
here
the
x minus
function u is square.
x minus
Square.
y, x y. And yes, if I consider this quadratic form, then there is square and dx dy. So there is greater.
No, it's sufficient, it's clear now.
Okay. So let us go back to this convergence. So we have to
I think 1/2 should be 1/2 in front of the
I consider here
mu over lambda. The weight is mu over lambda.
I consider here the weight.
And with this weight we have mu times mu.
So if I consider this weight, what does it mean? That if I consider the LUU, yeah, then there is integral over lambda x divided on epsilon, mu divided on epsilon dx, yeah? Sorry, yeah, mu, yeah, sure. Mu divided on lambda dx. Yeah, because there is our weight, our measure.
My question actually is probably completely stupid. I just forgot my functional analysis, but but why? So it means that resolvent exists for all real m except 0 are not on the spectrum.
The spectrum is negative.
But m is negative.
It's positive.
The spectrum is positive. The spectrum is
Spectrum is
positive.
positive. M belongs to the complex plane without the positive symmetry.
No, but so in that inequality m is
So, but okay, if it is positive. No, the spectrum of this operator is negative.
Okay.
So when we consider the quadratic form, we consider with minus.
M is positive, yeah.
M is positive. The spectrum is negative.
So the distance from the spectrum to M is equal to M, yeah.
At least, yeah.
At least M.
No, it's fine.
Okay. And so what we proved that U epsilon close to W epsilon and W epsilon tends to U0. So then we can conclude that U epsilon minus U0 tends to 0, right? Now we prove our convergence for function f from the Schwarz space, and then using that Schwarz space is dense in L2, we can...
Just density argument, yeah.
Yeah, we can...
And uniform a priori estimate.
Yes,
yeah.
yes. Okay, so now I finish the main part of my talk, and in the conclusion I'd like to say that what we can say about the corresponding semigroup. So we consider the corresponding semigroup in L2 with generator, because it is using the Healy-Yasuda theorem, we can prove, for example, that it is a generator of strongly continuous and contraction semigroup in L2. So we can consider operator T epsilon, E TL epsilon, and T0, which is TL0, yeah? In this setting, I'm sorry, there is... Yeah, and if we are interested in the corresponding behavior of this semigroup, we can prove the strong convergence. So we can prove that for any f, using, for example, our result, for any f in L2 showing. Not on the torus, because I know in yeah, sure, in RD, the following T epsilon TF tends to T0 TF for any T, or uniformly on any bounded interval on T.
When it's epsilon, respect to epsilon.
Yeah, when epsilon tends to 0. And in fact, that means that if we consider two parabolic problems corresponding, yeah, du epsilon dt L epsilon O is equal to F, and the same for the operator L0, du dt L dot. Then in this setting we can prove that U epsilon Tx minus U epsilon U0 Tx tends to 0 in L2 RD for any fixed T, for a fixed T, or again uniformly bounded but on any bounded interval. So in our case, when we consider the symmetric kernel, we have this result about convergence of the solution of the corresponding parabolic problem.
So this is a kind of what you said, central limit theory, yes?
Yeah, as you like, yeah, that's right.
So
Because there is density of the, yes,
so
density,
the
probability density at time
There
t.
is universal
Yes.
model which
Yeah.
theta should be defined.
Yeah, in fact, yeah, at time t. The invariance principle, it is more difficult step, but we also can, under some additional, a little bit more strong assumption on the kernel A, we can prove also the invariance principle, the convergence in the space of trajectories. But what I'd like to say that on the next lecture, on Friday, we'll see what happens when the kernel is not symmetric. So we don't assume that it is not symmetric, and in this case, I just only announce what's happened in this case. That we obtain the similar result, but with in the following form. Yeah, and the main question will be about this efficient drift B, how to define this drift, but the result will be very similar. Okay, thank you. Then I stop for today.